Hello, my name is Bob Swanson. I'm an ICC physical science instructor. I teach the physical science courses as well as astronomy and even a little hint of meteorology every now and then. Now, I may not be the instructor for your section of this course. This is Physical Science 2, and I may not be the instructor for your section, but I am the designer of this course. So we're going to be together for the semester as you learn about the wonders of Physical Science 2. Now, Physical Science 2, you may be taking this course after you took Physical Science 1. Physical Science 1, remember, was mostly physics with a lot of the math stripped out, and then a little hint of astronomy at the end. Physical Science 2 is essentially general chemistry with a lot of the math stripped away. And then later on in the course, we'll touch on topics such as geology and even get into a little bit of meteorology. Now, if you are taking this course and you took Physical Science 1, you may already have the textbook. This is the textbook. It's the Hewitt textbook. The first half of the book was mostly physics, and the second half of the book is mostly chemistry. We're going to be dealing with the second half of the book this semester. In fact, we're going to be starting in chapter 15, which is entitled The Atom. And, well, the atom we're going to get into is the basic building block of matter. One thing you'll notice when you turn to the first page of this particular chapter, you're going to notice a little explore thing. Well, it's a little activity for you to do. And so what you do is you get yourself a cup of warm water. Notice I've got a little W on there for warm, and a cup of cold water, a little C there for cold. And you have to get some food. Oh, you're not going to watch me do this, are you? You're going to do this yourselves, aren't you? That's why it says explore with an exclamation point. It's your job to learn about this. You have to be an active participant in your own education. So we'll talk about the results of this little explore activity a little later on, but for now, try it out, and we're going to delve a little deeper into these topics as we continue with the little videos.
What is the most astounding fact you can share with us about the universe?
The most astounding fact.
The most astounding fact
Is the knowledge that the atoms that comprise life on Earth, the atoms that make up the human body, are traceable to the crucibles that cooked light elements into heavy elements in their core under extreme temperatures and pressures. These stars, the high mass ones among them, when unstable in their later years, they collapsed and then exploded, scattering their enriched guts across the galaxy. Guts made of carbon, nitrogen, oxygen, and all the fundamental ingredients of life itself. These ingredients become part of gas clouds that condense, collapse, form the next generation of solar systems, stars with orbiting planets. And those planets now have the ingredients for life itself. So that when I look up at the night sky, and I know that, yes, we are part of this universe, we are in this universe, but perhaps more important than both of those facts is that the universe is in us.
By way of explanation, the voice you heard a couple of slides ago, that little video clip, was Neil deGrasse Tyson. He is the director of the Hayden Planetarium at the American Museum of Natural History in New York City. He's one of my science heroes, and he's an astrophysicist, and he was talking about atoms. Okay, we haven't really defined what an atom is, at least not here in the notes, but in your book, an atom is well, first of all, let's go back to its roots. It is Greek for indivisible. Indivisible. What does that mean? We know it from the flag, right? When we say the Pledge of Allegiance. Yeah. Indivisible, with liberty and justice for all. It cannot be divided any further. And this was a term coined by a Greek guy named Democritus, and he essentially said, if you take a chair or a desk or your house and you just start chopping it, chop it in half again, chop it in half again, chop it in half again, eventually you will get to a point where the piece that's left is so small that it cannot be divided. It is indivisible, and that's what he called an atom, the basic building block of matter. Now, if you have a material that is made up of only one kind of atom, we call that an element, because an element is made up of just those type of atoms. So, for example, gold. Now, a gold atom is different than a silver atom, or a copper atom, or a helium atom. So you can take a chunk of gold and chop it, chop it, chop it, chop it. Eventually you get down to one piece that is uniquely gold. And if you have a collection of these pieces that are all gold atoms, we call that an element. So an atom is on a really, really small scale. An element can quite often be what's called macroscopic, something that we can see with our eyes. Again, from the Neil deGrasse Tyson video, hopefully you picked up on the idea that all of the atoms that are in our bodies, first of all, they're different types of atoms. We've got a lot of hydrogen in us because we're mostly water, right? What is water? Water is just a couple of hydrogen atoms and an oxygen atom. But all matter is made up of atoms, and all atoms essentially are on the periodic table. There's 115. There's actually more. These are kind of dated notes. There's actually been more in recent years created, different types of atoms created. 90 are actually natural. And then the other ones that are on the periodic table are ones that have been synthesized in labs. And usually they're created for just an instant, and then they fall apart again. Those synthetic atoms, quite often are very unstable. They can't remain for very long. But 90 different types of atoms are found in nature. By far, the most common type of atom is hydrogen. Not only here on the Earth, but also in space. The universe is mostly hydrogen. Following that, helium. And then after that, it's lesser amounts of lithium and carbon, and the list goes on. The more complex atoms, as was discussed in the video, carbon and nitrogen and gold and iron and all those sort of things, the things that are in your body, the iron in your blood, came from the explosions of stars from long ago, when a star goes supernova. And if you take my astronomy class, we'll talk about how stars can create these heavier atoms, but they can only do that either during their lifetimes or most particularly at the end of their lives. When they go supernova, they create the very heavy elements. But all the elements will be found on the periodic table, which is something you're going to get to know very well this semester. Now, I mentioned this Greek guy, Democritus, and he said that you can take an object or anything and chop it down to an atom, and that's the smallest piece, the indivisible piece. And that's true to a certain extent. You can chop down a piece of gold down to one gold atom, and that's the smallest you can get, and be able to identify that object as being uniquely gold. If you chop down silver and get down to one single silver atom, that silver atom is different than the gold atom. But what Democritus didn't know is that you can actually keep on chopping. There are what are called subatomic particles. The one thing about subatomic particles that's different than, say, a single atom is that the subatomic particles are not unique. So, for example, if you take gold and you start looking within that gold atom, that single gold atom, you're going to find protons and neutrons and electrons. And a proton from a gold atom is indistinguishable from a proton from a silver atom or a proton from a carbon atom. So these subatomic particles are indistinguishable from each other. But as we're going to learn, protons are in what's called the nucleus. They're very massive. They have a positive charge. Electrons are not in the nucleus of an atom. They're in what's called the electron cloud. They have negative charges, and they don't have very much in the way of mass. And neutrons are also in the nucleus of the atom. They do not have any charge, but they are quite massive. Protons and neutrons are referred to as nucleons. They are subatomic particles that are located in the nucleus of an atom. Okay, so in the previous slide, you may have noticed that atomic number is the number of protons in an atom. So for example, oxygen. Oxygen has 8 protons in its nucleus. An atom of oxygen has 8 protons in its nucleus and has an atomic number of 8. And if it doesn't have 8 protons in its nucleus, it's not oxygen. If it's got 7 protons in the nucleus, it's not oxygen, it's nitrogen. So each element is distinguishable by the atomic number, by the number of protons in its nucleus. Now, atomic number is different than mass number. Mass number is the total number of protons and neutrons in the nucleus, add them together. That gives you the mass number. So atomic number, number of protons. Mass number, number of protons plus number of neutrons. And atomic mass is the total mass of the atoms, the protons, neutrons, and electrons. And now electrons they have such little mass that they really are not a factor in the total mass. It's really just add up the number of protons, the mass of the protons, add up the mass of the neutrons, and you get the atomic mass. Atomic mass it's given in units of atomic mass units, which is essentially the mass of a proton. So atomic mass is different than mass number. Mass number is different than atomic number. Again, atomic number, number of protons. Mass number, number of protons plus number of neutrons. Atomic mass is the total mass of the atom. Okay, if you're still hanging with me, if you've been going through the questions here, or going through the slides and been doing the questions that are kind of along the way, these little check your understanding questions, now might be a good time to go ahead and tackle the skills tests for this module. You're going to find these under modules, module 1. When you click on skills test, you're going to see this little screen. It gives you a link to the actual activity. You can click on build an atom. That's going to take you to the quiz. And then I encourage you, especially if this is the first time you've taken a course like this, don't forget about these tutorial videos. These essentially will walk you through the activity. It's a very quick video. This one's only 3 minutes and 14 seconds. It essentially describes what you'll be doing in the build an atom activity. Similarly, when you do the atomic structure, again, I encourage you, watch the video first. It's only a minute long, but it's going to help you work your way through the interface so that you don't get too frustrated. I want you to learn the concepts here. I don't want you to get so bogged down in learning the interface that you lose sight of what we're actually trying to learn here. So I encourage you, watch the videos first, then tackle these skills tests. Okay, so one thing that's very important to understand is that where have we come so far? We know what an atom is, we know what an element is, we know something about subatomic particles. Now the next step, and this is a very important step because this is something we'll be using really throughout much of the rest of the course, is the periodic table. Now the periodic table is essentially a listing of all the known elements, both natural and man-made. One thing that's very important for you to understand is that the periodic table need not be memorized. You don't need to memorize it. You need to know how to use it or how to read it. And it's very similar to a dictionary. You don't need to memorize the dictionary, but you need to be able to use it. You need to be able to find a dictionary and look up a meaning of a word. You need to know maybe perhaps how it's pronounced or its language of origin or something of the sort. Same thing with what a chemist does in using the periodic table. You don't need to memorize absolutely every factoid. We'll have periodic tables at our disposal, either in the book. There's also an online version of the periodic table we'll be using for a lot of our activities. Don't need to memorize it. You do need to know how to read it. One of the first things you'll learn about the periodic table is that we can essentially break the periodic table into 3 different sections. The oranges here are all what are considered to be metals. And even hydrogen. Now hydrogen it's kind of a funny element in the sense that it only acts as a real metal under special conditions, and actually conditions that typically aren't found here on Earth. So hydrogen, it's listed in the metals. It doesn't necessarily behave like a metal unless you're like on Jupiter, for example. But all that aside, the orange elements are metals. The green ones here in the middle, this little stair-step area, these are what are called metalloids. Sometimes these are called semiconductors. And then finally, you have what are called the nonmetals, these pink elements. And we'll be talking more about the different properties of these different breakdowns of the elements as we move on. Okay, so the periodic table is laid out in a bunch of columns and a bunch of rows. One thing you should know is that vertical columns are called groups, and horizontal rows are called periods. So as we see in this depiction, there are 18 groups, or there are 18 columns, and then there are 7 periods. Now, quite often you'll see the way the periodic table is laid out, you'll see kind of a broken off area. These are extra elements. They're called the lanthanides and the actinide series, and they actually do fit in right in here into the periodic table. Of course, that would make if we put them in there, the periodic table would become very, very wide, and so therefore it's usually just kind of they're thrown in to the place below the rest of the periodic table, even though they're actually part of periods 6 and 7. Okay, so like I said earlier, the periodic table is not to be memorized, but it is important to understand trends in the periodic table. And this is one trend that you're going to notice in the periodic table is this is essentially atomic radius size, essentially the size of the atom. And you notice there's a couple of trends. Notice that as we go down each group, notice anything about the size. So let's say as we go from hydrogen here down to rubidium, or if we go from carbon to selenium. What do you notice about the size of those balls? They get bigger, right? So that tells us that the average size of the atomic radius increases as you go down most groups. How about when you go from left to right across the periodic table? When you go across a period, notice any trends here? Not quite as clear-cut of a trend, but there is sort of a trend that typically your elements way to the left on the periodic table have relatively large radii compared to your elements on the right side of the periodic table. So rubidium is much larger, rubidium, Rb, much larger than xenon, for example. The next step is to understand why. Ask yourself why do we have these differences in the size of the atom, and why do we have these trends that show up in the periodic table? Okay, moving beyond that, one thing, we've already kind of broken down the periodic table into metals, metalloids, and nonmetals. You'll also from time to time hear certain groups being called certain kind of common names. So group 1, those are typically called the alkali metals. Group 2 are quite often called the alkaline earth metals. In between there, anywhere from groups 3 through 12, these are all considered your transition metals. And those include your actinide and your lanthanide series, the ones that are placed below typically. And then as we get way over to the right side, your group 17 elements are called the halogens, and the group 18 elements are called the noble gases. And again, here's those transition metals we call the inner transition metals of the actinide and lanthanide series, placed typically below the periodic table. Okay, now here I wanted to bring up a very important point. One of the difficulties about chemistry, both teaching and understanding chemistry, is that it takes place at a very microscopic level. So it's unlike physics. Physics, when we talk about throwing a ball, going through projectile motion or friction, we've touched all these things. We sort of understand them. When we talk about astronomy, for example, that's another course that I teach. It's kind of easy to understand some of it because you can actually appeal to physical models. So for example, a lot of us have done a science fair project where you've made a model of the solar system. And it's essentially just kind of replicating the solar system, but at a much more convenient scale. The solar system is huge, but we can kind of show the different distances between planets and the size of the planets if we just change the scale. But that's because we can actually see these objects. When we deal with chemistry, when we start talking about atoms and protons and neutrons, these are things that we certainly don't see with our eyes. And we don't even see with quite often like optical microscopes. Optical microscopes use the wavelengths of visible light, which are too big to see atoms. So in order to quote unquote see atoms, we have to use other things like scanning tunneling microscopes that use a different, they don't use the visible wavelengths of light. So for the most part, what we have to do when we're thinking about chemistry and teaching chemistry is we have to appeal to conceptual models. This is not really what an atom looks like, but based on the way atoms behave when they interact with each other, we sort of know kind of what they look like. So it's more of a conceptual model. So for example, here's an atom. And we know there's a nucleus at the center of an atom. But as far as like the electron shells or the electron orbits or the electron cloud, it's not necessarily that well known. But we do know there are certain energy levels outside of the nucleus where electrons tend to reside. And so we represent these distances in shells. So quite often in two dimensions, you'll see kind of rings. And this is what's called the Bohr model of the atom, where you kind of imagine electrons being little planets going around the nucleus that's the sun. Well, it's useful to a certain extent, but don't marry yourself to think that that's really what it is in reality. In 3 dimensions, the Bohr model winds up looking like these shells, but even that must be taken with a grain of salt. I shouldn't mention these numbers here. That's the number of valence electrons permitted in these different electron levels. So in the first valence shell, 2 electrons, 8 electrons in the next, 8 electrons in the next, etc., etc. But it's useful to note that the nucleus is at the center. It's useful to know that the electrons are outside of the nucleus in essentially a cloud, and that cloud has certain energy levels. But again, don't get too married into the idea that this is actually what an atom looks like. It's not. This is just a conceptual model, which makes it easier for us to understand how atoms interact. Now that you've gotten through most of the Module 1 material in this lecture, I do encourage you to move on to the lab activity. Now again, this is found under Module 1 in Canvas, and there's a link here to the introduction to the periodic table. It's actually a little quiz. There's a video that actually accompanies this that you'll watch, then answer some questions about it. Again, I encourage you to check out the tutorial, which will help you help you understand where you find the video and then how to answer the questions that go along with the video. So again, Module 1 lab activity is your next stop. Another thing you may want to check out is at the end of your chapter, chapter 15, there's something called a Readiness Assurance Test. And for whatever reason in the textbook, they didn't put the answers in there. So I encourage you, every time you get to the end of a chapter, to make sure you understand the material, go through the Readiness Assurance Test. Unfortunately, like I said, there's no answers in the book. A lot of folks like to know whether they're right or not. So when you've gone through the test, now check yourself. Here's your answers to Chapter 15's Readiness Assurance Test. Okay, so if you didn't try this one yourself, here's the Explore activity from Module 1. And what we've got here is we got 2 cups of water, cold water on the left, warm water on the right, and we have about equal amounts of water in each cup. Now the task, they tell you to do a couple of drops of food coloring in the cold first, watch it disperse, and then compare it to the warm. We're going to do them both essentially at the same time. So I'm going to put about put 2 drops of food coloring in the cold water. I'll do the same thing to the warm. Let's see if we notice a difference in the amount of time it takes for the food coloring to disperse throughout the entire cup of water. Notice the difference? I think it's already pretty apparent, and I'm just going to let it sort of time lapse, and we'll wait till essentially all the food coloring has dispersed. So there you have it, friends and neighbors. Notice the Making Generalizations question says, what can you say about the motion of the molecules that make up the food coloring? Well, that's up for you to answer.